Hello, everybody. Welcome to our final class of the week. I see a few of you are here. I see a few of you are here already. Navik with the first like before class even started. 10 minutes before class started. Good morning, William. Yeah, so let me know who's here. Say hello. And then we'll get started in a few minutes. Good morning. Oh, Emma has switched her account, I see, under her sister's account. Taylor, good morning. Good morning, Sarah. Good to see you here. Good morning, Cal. All right, about a minute, we'll get started. We're going to start by finishing up the example we couldn't quite finish at the end of yesterday's class. That's actually not how we're going to start. We have something else that's more important to do at the beginning. All right, well, it's 9 o'clock, so we could get started. So if anybody wants to join in the simultaneous sip, we could do that. It's our last one of the week, so hopefully you are prepared. Yeah, so let's do the simultaneous sip. Yeah, so let me know in the chat if you joined in. I mean, I guess it doesn't have to be your last one of the week. If you want to stay and watch my calculus class, you could get another one. Looks like a few of you joined in. That's nice. Okay, so we have this example. We've sipped. Right, we had this example where we first showed that U1, U2, and U3 formed a orthogonal basis. And now we want to express y as a linear combination. So we want to express y as C1U1 plus C2U2 plus C3U3. Right, that's our goal here. And we have methods to do this using our old, like, what we did at the beginning of the semester. Right, we can put this as an augmented matrix and just row reduce, and that would give us our answer. But we'll see that since we have an orthogonal basis, it's actually easier to just use the formula from the last theorem. So the last theorem told us that to get C1, so to get the coefficient of U1, we do y dotted with U1 over U1 dotted with itself. And right, we can just work out this calculation. Right, did anybody have any luck doing this last night, or do we just wait until today? It's fine either way. So when we do this calculation, the dot product of y with U1 is 18 plus 1 minus 8. That's our numerator. And our denominator is just 9 plus 1 plus 1. Okay, so our coefficient of u1 in this expansion is 1. We could go through and do the same thing for u2 and u3. So the coefficient of u2 is y dot u2 over u2 dotted with itself. So that's negative 6 plus 2 minus 8 in our numerator, and 1 plus 4 plus 1 in our denominator. It's negative 12 over 6. And then last, C3 is equal to y dot u3 over u3 dotted with u3. Our numerator is minus 3 minus 2 minus 28 over 1/4 plus 2 plus 49/4. And when we do the math out, we would get negative 2. So you can check that on your own. Hi there, Can. Nice to see you here. Okay, so yeah, just double check this on your own, but we're not going to go through that. We could conclude that y is equal to 1 times u1 minus 2 times u2 minus 2 u3. All right, so this gives us a quicker way to express y as a linear combination of these basis vectors. Another way to write this, so yesterday we said that S was equal to the set u1, u2, u3. That was part of the question yesterday. I didn't write it today. Another way to write this is that the S coordinates of y is the vector 1, negative 2, negative 2. So these are saying the same thing. Any questions or thoughts about this example, or are we good to move on? So just give me a thumbs up or thumbs down on how you feel. Okay, thumbs up, nice. Good, a few thumbs up. Yeah, so this is pretty straightforward, and dab, sweet, in the middle. Yeah, okay, so let's just kind of go through one quickly. We had our theorem that told us how to compute these C1 through C3. It's just basically to get the coefficients, you do this dot product. Y dotted with U1 over U1 dotted with itself. Evaluate it, and that tells us the coefficient. That tells us the value of C1. Similarly with C2 and similarly with C3. So this was the theorem we ended class with yesterday in action. And I have a YouTube video going through another question like this that will be out tomorrow. So take a look at that if you need a little bit more practice with this. But we're just applying a theorem, which tells us exactly how to compute these coefficients. Okay, so now we're going to talk about an orthogonal projection. Okay, so this is again something you may have seen in your Calc 3 class, but we're going to, I'm going to assume that you have not seen this before. So we're going to start with the basics. So given a non-zero vector, U in Rn, consider the problem of decomposing a vector y in Rn into the sum of two vectors. Okay, so we want to write y as sum of two vectors. And we'll sketch a picture of what we're talking about in a second. We want one of them to be a multiple of u, and we want the other one to be orthogonal to u. Okay, and again, we'll get to a picture in a second. But yeah, so just to kind of read what we wrote here, we want to take a vector, just some arbitrary vector in Rn, and express it as a sum of two vectors. One of them is going to be a scalar multiple of u, so it's going to be parallel to u. The other one is going to be perpendicular to u. Okay, so that's our goal here. So what we're saying is we wish to write y as y hat plus z, where y hat is equal to alpha u, and z is orthogonal to u. Okay, so this is kind of in math terms what we want to do here. Okay, so let's get a picture going. So let's say we're in R2. Okay, it's easiest to draw in R2. And let's say that y is this vector up here. And we'll say that u is the vector here. Okay, so what we want to do is we want to figure out a way, and so we haven't really done anything. This is just kind of the problem we're trying to solve. We want to figure out a way to it's a little bit so this vector here is going to be a scalar multiple of u. This would be the vector alpha u. And then to get from alpha u up to z, to y, we'll add this vector z. Okay, so that's our idea, is we want to figure out what is this vector and what is that vector. Okay, and so let's try to figure out how to get alpha. So we could solve for z here. So z is equal to y minus alpha u. And this is orthogonal to u. Okay, so my question for you before, so I'm going to kind of stop writing for a second, give you a chance to catch up. But here's the question. So z is orthogonal to u. So what can we say about z and u? Yeah, their dot product is 0, right? That's what it means to be orthogonal. So let's just take their dot product and that will help us find alpha. So z dotted with u is equal to 0. Well, that's equal to y minus alpha u dotted with u. Right? And now our goal is to solve for alpha here. So let's distribute this dot product through. So 0 is equal to y dot u minus alpha u dot u. And so we can solve for alpha. Alpha is equal to y dot u over u dot u. So we have thus y hat, which is the part that's parallel to u, is this scalar times the vector u. Okay, so to figure out the vector that is parallel to u, we have to find y dot u over u dot u. This is the exact same ratio as what we dealt with these coefficients, and that's not a coincidence. Okay, so let's give this a name here. Okay, so let L be the subspace spanned by U. Okay, so L in our drawing here would be, the line that goes through the origin in the direction of U, and it goes on to infinity and negative infinity. Okay, so let L be the subspace spanned by U. The orthogonal projection of Y onto L is the vector projection onto L of y, which is equal to y hat, which is equal to y dot u over u dot u in the direction of u. Okay, so what this tells us, so again, we're going to take a vector, we're going to express it as a sum of two vectors. One is parallel to u, the other is perpendicular to u. And this tells us the parallel component. Okay, so what it does is it takes our vector y and puts it down onto this subspace L, which is a line. Okay, so let's take a look at an example. And again, ask any questions that if there's something you need me to clarify. And before we get to the example, if I lose track of time, and it's like past 9:40, let me know because you guys have the quiz at 9:40. So I don't want you to lose any time for that. All right. Okay, so the example is let y be the vector 7, 6, and u be the vector 4, 2. Find the orthogonal projection of y onto u. So that's the first part. And then express y as the sum of two orthogonal vectors. One in the span of u, one orthogonal to u. Okay, so I'll give you a minute or so to try to work this out. Does somebody want to comment in the chat how they plan to start this question? If they have any thoughts, could help your classmates out. Okay. So we want to find the orthogonal projection of y onto u. Okay, I guess this should really be like the subspace spanned by u, but it's all talking about the same thing. So it's asking us to find y hat. Yeah, so find y dot u and u dot u to find the vector parallel to u. Yeah, exactly. So we're gonna find y hat using this. So the dot product of y and u is 28 plus 12 in the numerator. And u dotted with itself is 16 plus 4. So this is 40 over 20, which is 2. So we get 8, 4. That's our parallel component. And then to get to the perpendicular component, you're right. What Taylor said is exactly right. Subtract. So we want z here. Z is the orthogonal component. So z is equal to y minus y hat. 7, 6 minus 8, 4. Which is negative 1, 2. So we could write y as 8, 4 plus negative 1, 2. So this is the y hat. This is what we call z. And if you were to plot this, if you were to graph y and then these two vectors by hand, attaching z to the endpoint of y hat, you'll get a picture that's very similar to what we have here. Okay, so I'll just do a quick sketch of what this would look like. It's not going to be perfect, but the computer could do a better job. All right, so 7, 6 is like the vector that's out here. 4, 2 is here. So L is the line that goes through the origin in the direction of u. So y hat would be here, the vector 8, 4, and then z would be the vector negative 1, 2. So the drawing, I think, does a pretty good job of showing what's happening here. So let's continue with this example. Find the distance from y in this previous example. Find the distance from the vector y to the line L. So does anybody have any ideas of how we could do that? Yeah, it's just the length of z, right? So y hat is going to be the closest point on L to y. And so we just look for the length of z. Yeah, another way to think of it is it would be the distance between y and y hat. So this is the distance. Okay, and the way z was found, it's just the difference between it's just the vector that goes from y hat to y, or the length of v. Sorry, z. Okay, so to get the length of z, that's the square root of the entries of z squared. So our vector y, or the endpoint of y, is square root of 5 from L at its closest point. Okay, so now we're going to look at a special type of orthogonal basis that's called an orthonormal basis. And we're going to see that if we have an orthonormal basis, a lot of our calculations will be made very easy. And again, if you have any questions, just throw them in the chat and I'll answer them when I see them. So a set U1 through UP is an orthonormal set if it's an orthogonal set of unit vectors. Okay, so my question for you, what is a unit vector again? Right, we know what an orthogonal set is. Each of the component-wise dot products is 0, but what's a unit vector? Anybody have any guesses of what a unit vector is? If you're unsure, saying unsure is also fine. I'll remind you. Yeah, a unit vector is a vector whose length is 1. Okay, so we're going to have, so an orthonormal, so notice it says orthonormal now instead of orthogonal. An orthonormal set is an orthogonal set, so they pairwise dot product is 0. each of the vectors has length 1. Okay, and if W is the subspace spanned by such a set, we say that U1 through UP is an orthonormal basis for W. Okay, so let's look at an example. Well, before we get to an example, can anybody think of an orthonormal basis for Rn? Do we have a collection of pairwise perpendicular vectors that are all of length 1 that span Rn? I'll answer this because we're kind of low on time. The standard basis, the E1 through E, yeah, the columns of the identity matrix, Taylor. So right idea. So is the standard basis. Remember, these were vectors that had zeros for all of their entries except for one of them had a 1. One of the entries had a 1. Like E1 had a 1 in the first entry, E2 has a 1 in the second entry, and so forth. So it's not hard to show that they're all perpendicular to each other, and it's also not hard to show that their length is 1. Okay, so let's look at this example. So we'll show that V1, V2, V3. Hey, it's Emma's sister. Am I late? A little bit. We've had students that show up later than this. So show that V1, V2, V3 is an orthonormal basis. For R3. V1 is the vector 3 over square root of 11, 1 over square root of 11, 1 over square root of 11. V2 is the vector minus 1 over root 6, 2 over root 6, and 1 over root 6. And V3 is the vector minus 1 over root 66, minus 4 over root 66, and 7 over root 66. Okay, and I'm just going to work this out now. Since we're kind of running low on time. Once it hits 9:40, and if you're in the 9 o'clock class, you're free to just peace out. But if you want to stay until I finish the end of this question, that's also fine. But this will be uploaded to YouTube immediately, so you could just see how it's finished by checking it out on YouTube. But what do we want to do? We want to first show that it's an orthogonal set. So we have to show pairwise dot product is 0. And then we want to show that each of the vectors has unit length. So basically what we want to do is compute V1. We basically want to show V1 dot itself is 1, V1 dot 2 is 0, V1 dot 3 is also 0. Similarly, V2 dotted with itself is 1, and V2 dotted with the other 2 is 0, and is equal to -3 over root 66 plus 2 over root 66 plus 1 over root 66, which is equal to 0. V1, V3 is equal to -3 over root 726 minus 4 over the same denominator plus 7 over the same denominator, which again is equal to 0. And V2 dotted with V3 is 1 over root 396 minus 8 over the same denominator plus 7 over that denominator, which again is equal to 0. Okay, so it's clearly an orthogonal set, right? Because it's pairwise dot products are all 0. Now we just want to show that when you dot it with itself, we get 1, right? Sure, we should be taking the square root of when you dot it with itself, but since we're looking for 1, the square root of 1 is 1. So we could just dot it with itself to check what we get. Again, if those of you in the 9 o'clock class, you're free to start your quiz now, but maybe you want to stay and watch this. You have an hour to do it. It's going to take you 5 seconds. So V1 dotted with itself is 9 over 11 plus 1 over 11 plus 1 over 11, which is equal to 1. So V1 has unit length, right? If we took the square root of the dot product with itself, we'd get the square root of 1, which is 1. V2 dotted with itself would be 1 over 6 plus 4 over 6 plus 1 over 6, which again is 1. And then last, V3 dotted with itself be 1 over 66 plus 16 over 66 plus 49 over 66, which is equal to 1. Okay, so let's just kind of conclude. We've done all the work. Now let's just write down what we've done. So V1, V2, V3. Is linearly independent since it's an orthogonal set, right? We showed that yesterday. It was one of our theorems. Any 3 linearly independent vectors in R3 is a basis. Right, that's the dimension argument. So we showed it's a basis, and each vector has unit length. So we can conclude that V1, V2, V3 is an orthonormal basis for R3. Okay, that seems like a good place to stop. I will, let me get out of the screen here. Whatever. Okay, I'll post some homework, hopefully this afternoon, covering 6.1 and the beginning of 6.2, or what we've gotten through in 6.2. There's still a little bit left of 6.2. But hopefully it's pretty straightforward. We're currently in the process of grading your exams, so those should be up this weekend. Yeah, so I'll stay around and answer any questions you have. But if you're in the 9 o'clock class, you should probably just do the quiz now and submit it to Canvas. Yeah, remember to hit the like button on your way out. That's so important, especially when you have a quiz coming up. It's like a guaranteed good luck. It's guaranteed good luck to do that. So yeah, so it's very important. But if not, have a good weekend. Stay inside. If you have to go outside, cover it up, wear a mask. Come on, I know you all have a scarf or something you could wear. We behave ourselves for a few more weeks or a few more months, and we'll be back at campus in the fall. Fingers crossed. Okay. I will see you on Tuesday. No class tomorrow. We have a spring holiday. Some would call it Good Friday. Yeah, I'll have office hours on Monday if anybody wants to ask homework questions, but yeah, hopefully it's pretty straightforward. Okay, bye-bye.